In this module, we will consider fluid mechanics. Fluid mechanics deals with the behavior of fluids and gases. Liquids and gases are composed of large numbers of microscopic interacting atoms and molecules, but instead of directly following the behavior of countless particles following Newton's laws, we instead approximate the fluid as a continuous medium. We will consider the behavior of a fluid at particular points in space as the fluid flows. This is known as Eulerian fluid mechanics. But it is also possible to follow specific elements of the fluid as they move about, something known as Lagrangian fluid mechanics. At any given point in space, we will consider various physical properties of the fluid. Velocity is the first, and this is a familiar quantity. It is simply the rate and the direction with which a fluid flows. Second is density. Because we are dealing with a point within a continuous fluid, it turns out to be more natural to deal with density than with mass directly. And finally is pressure. Again, it turns out to be more natural to deal with pressure rather than force. Pressure is a measure of force as it is distributed over a given area. Most fluids are isotropic. This means that any force exerted on them is evenly distributed in all directions through the fluid in the form of pressure. In our scientific units, the units of pressure are given in terms of pascals. These are newtons per meter squared or kilograms per meter second squared. But again, we use the name Pascal and abbreviate it with capital P lower a as the symbol for the unit. Now, pressure is often measured in terms of atmospheres, which are defined as the average pressure of Earth's atmosphere at sea level. And 1 atmosphere is approximately 1.013 times 10 to the 5th pascals. It is common for pressure measurements to be given as gauge pressure, meaning that this is the deviation from the ambient atmospheric pressure where the measurement is made. This is in contrast to absolute pressure measurements, and in fact, the absolute pressure at a given point would be the gauge pressure plus the current ambient atmospheric pressure. Fluid mechanics is usually divided into 2 cases. First is hydrostatics, which is the study of fluids at rest. And second, hydrodynamics, the study of fluids in motion. When fluids move, they are said to flow. If the flow is not too fast, then it can be smooth, in which case it is called laminar flow. If the flow is too fast, on the other hand, then the flow near fluid boundaries becomes unstable and may become turbulent. With laminar flow, the fluid may flow with different speeds at different places, but layers traveling at different speeds slip stably past each other. Streamlines represent the paths of individual elements of fluid, and they never cross. The illustration here shows laminar flow of a fluid around some circular object, and the lines are each streamlines of the fluid flow. When turbulence sets in, the layers of the flow begin to mix. Streamlines in unstable regions swirl together, become poorly defined, and seem to intersect. Now let's consider hydrostatics. With any fluid in hydrostatic equilibrium, we can imagine any arbitrary subvolume. For example, consider the following cylinder or parallel pipette of height h and cross-sectional area A. The sum of all forces acting on that subvolume must sum to be 0. This subvolume will have a mass, m, given by the density of the fluid times the volume of that subvolume, which is A times h. Now imagine the top of the fluid is at the ambient atmospheric pressure, which we will denote by P naught, and so there is going to be a force acting down on the top surface of this subvolume. And that force is going to be equal to the ambient atmospheric pressure P naught times the area of that surface. At the bottom of the subvolume is going to be another surface. It's going to have a force acting up on it, which will be equal to the pressure at that depth times the area of that surface. And since the sum of all the forces acting on that subvolume must add up to be 0 for this to be in equilibrium, we have that the F sub P at the bottom minus F sub P naught at the top minus the weight of that subvolume of fluid must sum to be 0. This means that the pressure is going to change with depth. In hydrostatic equilibrium, pressure must increase with depth in order to support the weight of the fluid above it. In hydrostatic equilibrium, any subvolume of fluid, regardless of its shape, is supported by pressure from the surrounding fluid in precisely the right way to keep the subvolume in equilibrium. In other words, the integrated pressure over the surface of the subvolume provides a net upward force equal and opposite to the weight of the fluid in the subvolume. This leads us to Archimedes' principle, which says that the magnitude of the buoyant force experienced by an object immersed in a fluid is equal to the weight of the fluid displaced by that object. So if we just imagine the subvolume there, and imagine that it's still the same fluid, there is a buoyant force equal to the weight of the subfluid, and it just sits there in equilibrium. But if we replace that subvolume by some other object, then if it has the same shape as that subvolume, the buoyant force acting up on that object is going to be the weight of the fluid that has been displaced by the object. The net force acting on that object in the fluid will be its weight minus the buoyant force. In hydrodynamics, we will consider some simplifying assumptions. First, in order to keep things simple, we're only going to consider stationary laminar flow. That is, the velocity at any point in the fluid remains constant, and this kind of fluid is said to be irrotational. We'll also consider only what are called incompressible fluids. That is, the density of the fluid is constant regardless of the pressure. And we will also only consider non-viscous fluids. That is, there is no friction to the flow, so neighboring streamlines can flow at different speeds without affecting each other. As we consider hydrodynamics, let's first consider the consequences of having an incompressible fluid. If we restrict the flow of an incompressible fluid through some kind of piping, then the rate at which fluid flows into the pipe must be equal to the rate at which it flows out. We represent the rate at which fluid flows into the pipe as the time rate of change of the mass going into the pipe. Similarly, the rate at which it flows out is dm sub out dt. And these two rates must be equal. Now, at the input end of the piping, we assume that it has a cross-sectional area of A sub n. And now let's consider an infinitesimal thickness, dx. The amount of mass in this little volume, dmn, is the density of the fluid times the cross-sectional area, an, times the thickness of that little bit of area, dx. So that means that the rate at which fluid is flowing into the pipe is going to be given by the density of the fluid times the cross-sectional input area times the velocity with which the fluid is flowing into the pipe. We can do the same thing at the output end of the pipe. It has a cross-sectional area of A out and a velocity V out, and we see that the rate at which fluid flows in, density times area in times velocity in, must be equal to the rate at which fluid flows out, density times A out times V out, which gives us what's called the continuity equation, which says that for steady flow of an incompressible fluid, the input area times the velocity with which fluid flows in is equal to the output area times the velocity with which fluid flows out. Now, just to be clear, we don't actually need a physical pipe for this equation to hold. It is enough to consider any imaginary boundary with the restriction that the streamlines of the fluid flow do not cross the imaginary boundary except at the openings that we have in this case labeled with AN and A out. We can also use energy arguments to further understand simple fluid flow by considering any continuous subvolume of fluid as a system. We'll consider again a piping, and at the input of the piping we have cross-sectional area A sub 1, a pressure P sub 1, and an input velocity V sub 1. And at the output end of the pipe, we'll have a cross-sectional area A sub 2, a pressure P sub 2, and a velocity V sub 2. Now, this fluid is going to flow some distance, but we're going to assume here that the areas of the pipe are different, and so the length of the flow is going to be different at the two ends. At the input, it's going to travel a distance delta x1, and the fluid is going to travel at the output end a distance delta x2, but by continuity, the volumes in those two regions must be the same. Now, first we want to consider the work done by pressure as this fluid moves. So the work done by pressure is going to be force times distance, which at the input end is going to be the pressure times the area times the distance that the fluid moves. Okay, so this is P1 times A1 times delta X1. And since the force is acting in the direction in which the fluid is moving, it's a positive work done on the fluid at that end. At the other end of the pipe, the fluid is moving out and the pressure is acting against this. So the pressure and therefore the force are going to be acting in the opposite direction to the motion, leading to a negative amount of work being done on the fluid by the pressure. Now, internal, there is also pressure present anywhere we consider inside this continuous subvolume. But at any given point, there's pressure acting in both directions, and so there's no net work done on the fluid inside of that subvolume. So the total work done by pressure on this subvolume is the pressure difference between the two ends multiplied by delta V, the amount of volume which has moved from one end to the other. Remember by continuity that A1 delta X1 is the same as A2 delta X2, which is simply our volume delta V. Now, by the work kinetic energy theorem, we know that the work done by pressure is going to be equal to the change in the kinetic energy plus the change in the potential energy of the fluid. We lose kinetic energy from the fluid that leaves the lower end of the pipe, but gain some from the upper end. So the change in the kinetic energy from this displacement of the fluid is going to be given by 1/2 times the mass which we're gaining at the top end, which is rho delta V, times V2 squared, minus 1/2 times the mass which is leaving the bottom end, which is rho delta V again, times the square of the velocity V1 at the input end. Similarly, the fluid has a change in potential energy. That change in potential energy is going to be given by the mass which is moving from the low end to the high end, rho delta V, times g, times the change in the height, y2 minus y1. And putting this all together, we find that P1 minus P2 delta V, the work done by pressure, is equal to this change in kinetic energy plus change in potential energy. Now, we have delta V occurring in all places, so we can cancel this out. And we wind up with an equation which says that the pressure plus 1/2 rho times the velocity squared plus density times the acceleration of gravity times the height on one side must be equal to the same quantities on the other side. What this is saying is that this combination of quantities, pressure plus 1/2 rho V squared plus rho Gy, is a constant throughout the fluid. This is what's called Bernoulli's equation. Under our assumptions of steady, laminar, incompressible, non-viscous flow, any flow can be understood in terms of the continuity and Bernoulli equation. Moreover, in the case of hydrostatics, where the fluid speed vanishes, Bernoulli's equation reduces to our simple equation for pressure. To see this, consider the following. At the depth where we define y to be 0, the constant in Bernoulli's equation is simply the pressure there. At some height h above this, the constant in Bernoulli's equation will then be equal to the pressure at this height in the fluid plus rho gh. And this is simply our equation for hydrostatics. Now let's consider an example in hydrostatics. Mercury is poured into a U-shaped tube as shown. The left arm of the tube has a cross-sectional area of A1 equal to 10 square centimeters, and the right arm has a cross-sectional area A2 equal to 5 square centimeters. 100 grams of water are now poured into the right arm as shown. A. Determine the length of the water column in the right arm of the U-shaped tube. To find the answer to part A, we realize that the mass of the water which has been poured into that right-hand side of the tube is going to be given by the density of water times the cross-sectional area A2 times the length of that water column. So we can simply find the length of the water column as the mass of the water divided by the density divided by the area, which turns out to be 20 centimeters. Part B of the problem now asks, given that the density of mercury is 13.6 grams per cubic centimeter, what height, little h, does the mercury rise? Notice that in the left-hand diagram, when there's nothing but mercury, the mercury level on both sides is the same. But when we pour some water into the right-hand column, it displaces the mercury down, and that mercury must now occupy a volume in the left-hand column above its original level. Now, what is common to the left and the right-hand sides is that the pressure at the top of each column of fluid is going to simply be the atmospheric pressure there. When there was only mercury in the tubes, because we have a single fluid, the levels of mercury on the two sides is going to be the same. But because water has a different density than mercury, when we pour it into the right-hand side, the top levels of the water and the top level of the mercury on the left-hand side will not be the same. However, if we go down to the level at which the water and mercury meet, the pressure here, which we'll denote by P sub W, will be the same between the left and the right-hand columns, because between those two heights there is nothing but mercury below. Now, we also know that the volume of mercury, which has now moved above the original level of the mercury, that is the area A1 times little h, is going to be equal to the volume of mercury, which was displaced by the water, which is given by the volume capital H times A sub 2, capital H being the level to which the mercury has dropped in the right-hand side of the tube. Now, from Bernoulli's equation, we know that for the left-hand side of the tube, Pw, the pressure at the bottom of the column of water, is equal to atmospheric pressure plus the density of water times the acceleration of gravity g times the height of that column of water, capital L. But this will also be equal to the atmospheric pressure plus the density of mercury times the gravitational acceleration times the height of the column of mercury in the left-hand side above the level where we define Pw, that is little h plus capital H. From the continuity of the displaced mercury, we can replace capital H in terms of the ratio of the areas. Now we notice that the atmospheric pressure cancels from the two sides, and if we use the relationship between the mass of the mercury and its density to replace the density of mercury, we wind up with the following equation, which we can simplify to give us that the height is equal to the mass of the water divided by the density of mercury times the sum of the two areas. Plugging in numbers, we find that the mercury rises by a height of 0.490 centimeters.